Steinhauer here. Welcome back. We are wrapping up our discussion of black holes from the previous class. And I mentioned that no light can emerge from a black hole, but it turns out that other things can emerge from the surroundings of a black hole. And one of those things is called gravitational waves. These things are kind of difficult to understand, but anytime that a massive object is accelerating in space, it actually can cause ripples in space-time that can ripple away and affect things much farther away. So in this case, you see an image in the middle of two black holes. There they are, orbiting one another. And as they orbit one another, they're both accelerating, and both of them are causing these ripples to go out. And you see those ripples propagating outwards through space like this. This is not anything related to light. These things will travel at the speed of light, we think, but these are ripples in the fabric of space-time itself, these gravitational waves. And so if you have objects that are massive enough, that are accelerating fast enough, then we can actually have a chance to detect these things on the Earth. How would we go about doing that? Well, here first is an example of what would happen on the Earth when a gravitational wave passed by. Here is a quick animation to show you. So here you have what was a perfectly circular ring of particles. And as a gravitational wave passes by, it physically stretches and squeezes the positions of those objects as the gravitational wave goes by. And in this weird stretch, squeeze sort of notation. So how do you know that a gravitational wave is going by? Well, you can observe a ring of particles do this, or you can observe the distances between two distant objects change slightly as this wave goes by. Let's think about how we actually do this in practice. Here is one of the LIGO observatories. LIGO is short for the Laser Interferometric Gravitational Observatory. And this is a giant laser facility. So I don't know if you can see this very well, but this is the station where the lasers are generated and also detected. And this is a 4-kilometer long arm. And there's a mirror hanging in this end of the arm, and there's another mirror hanging in this end of the arm. And they have stationed these mirrors to be extremely precisely stationary. And so that we can tell if the mirrors get closer or farther away from each other by a fraction of the size of an atom. It's that good. And so there's one laser arm that goes this way, and there's a perpendicular one that goes off this way. And by using a technique called interferometry, we can very precisely measure any very tiny changes in the relative lengths of those two arms. And we're talking about, again, the sizes of much less than an atom's width. It changes in distance even over those long waves, those long arms, for the strength of the gravitational waves that we expect to be going by. Because again, just like light waves, the strength of a gravitational wave as it leaves will go down as 1 over r squared. So these things are very far away, and by the time they reach us, they're very weak. But if we have a high enough sensitive instrument, which we've built, we can actually detect them. Here is a schematic of how this works. You've got a laser being generated here, a beam splitter that sends half of the light this way and half of the light this way. These are highly reflective mirrors. Most of it is trapped in here, but some of it comes back then and can be recombined with this lever arm to give you your detector here and actually see an image. And so you can tell by the strength of that image whether things are changing on both of those lever arms. And so that's in practice how it's done. And so they've been working on this for decades and making gradual improvements. And finally, in January 2016, they found a signal that they believed. And so there's actually 2 of these LIGO instruments, one in Hanford, Washington, and one in Livingston, Louisiana, and they both saw the same thing. And that is the signature that you expect for 2 black holes merging. Now, 2 black holes are orbiting one another very closely. Why would they spiral into one another? Well, it turns out that these gravitational waves are taking so much energy away that that energy is taken from the orbital energy, and that will slowly cause these black holes to inspiral and eventually merge. And that's exactly what you're seeing here. The closer these two black holes get together, the faster they spin and the stronger the gravitational waves. And you can see the frequency starts out fairly low and then gets higher and higher and higher as these peaks get closer and closer together. And then they finally merge, and then there's some ring down, and then it's just a single black hole that isn't producing gravitational waves at all. And so the fact that both of these observatories found the same signal gave them high confidence that this was, in fact, an actual detection of a gravitational wave. Nobel Prizes awarded. Very exciting stuff. Of course, since then, we've discovered a lot more of these things. Here are just a few of them. This one, 62 total solar masses, black hole merger, 21 solar masses, and also how far away they are, 1.3 billion light years, 1.4 billion light years. This is way outside of our Milky Way galaxy, like vastly outside of our own galaxy. Like even a million light years is well outside our galaxy. A billion is 1,000 times further away from that. Here's another one, 49 solar masses. So just a schematic of some of the gravitational waves discoveries since the first one was discovered. Perhaps the most exciting detection that this one has made was this one in 2017. This one was exciting because it was not a black hole merger. It was two neutron stars merging. And again, the signal is weaker for this, but it was found both by the Washington site and by the Louisiana site and by one that's in Italy. Although obviously this one didn't see all that much. But it's still enough. This is a signature. Again, what are you seeing here? This is frequency as a function of time. So remember how it starts off fairly low frequency and then goes to high frequency. That's exactly what you're seeing here in phase space. The frequency gets higher and higher and higher, and you get a little chirp at the end as these two objects merge together. But this was exciting because it produced visible light also, right? Two black holes merging don't produce any visible light because light can't escape from either one of them. But it can escape from two neutron stars merging. And so this is the first gravitational wave source that had a visible counterpart. And you can see, this is the days after the LIGO triggered the event. You can see that the light that we received from this in various band passes and how that light changed over the first few weeks after this event went off. And you can see these are fairly faint magnitudes, again, bright up at the top, faint at the bottom. But this is probably the most well-studied event that has ever taken place in the history of the universe. Not only do we have this beautiful light curve information, but we have the gravitational wave signature to get very precise information on the actual masses of the neutron stars that were involved in this process. It was a very exciting event. One more thing I want to mention about black holes, and then we'll call it a topic, is Hawking radiation, named for the person who first proposed it by the name of Stephen Hawking. So Hawking radiation is a way that a black hole can lose mass. So even though nothing can escape from inside a black holes actually can evaporate over time and get smaller in mass. How does this work? Well, it's something called Hawking radiation, and the idea is this. Everywhere in the universe, you have particles and antiparticles that are sort of spontaneously forming and disappearing. Now, this isn't usually a problem. These pairs of particles will form, which actually requires a lot of energy, but they'll immediately annihilate one another, and you'll get that energy back. Something about the weirdness of the quantum soup that is the universe makes this possible. Now, when you happen to be very near a black hole, some weird things can happen. When you get this particle-antiparticle pair being created, the tidal forces of the black hole can rip them apart. And so one of them will fall into the black hole, and one of them can actually escape the black hole. And whichever one it is, it doesn't matter if it's the particle or the antiparticle, they have to carry energy away from that black hole. And so this is a way, even though nothing is coming from inside the black hole, it's a way for energy to be sapped from that black hole. And if you have a black hole that's in a very cold universe and nothing else is impacting it, black holes will eventually, over hundreds of million, over huge time scales, will eventually begin to shrink. Now, the bigger your black hole, the slower this happens. So if you have a very massive black hole, this is going to take an extraordinarily long time. We'll talk about this at the very end of the class. But a very small black hole will actually evaporate fairly quickly. So that's Hawking radiation, and it is a way that black holes can evaporate. And it ends our discussion of black holes. We'll come back in the next video and start to talk about the bigger picture of the universe. And we'll start with our own galaxy, the Milky Way.